At the moment, you might have noticed there's a heat wave going on. So apparently this is because of global warming. It's getting hotter and hotter. It's the hottest year on record, everything. So when exactly was the hottest year on record? It was 1995. Oh no, 2001, 2003. Actually, it seems that 2006 was the hottest in a million years. And every year we get this update of this year is the hottest year on record. And sometimes they'll even make claims like that it's the hottest in 100,000 years or a million years. You know, so this is a recurring news story, which is very easy to write. You just get your thing and you just copy and paste and then just change the date. So, but the question is, how do we measure the global temperature? Well, you know, it's obvious. Every year, the world's global climate scientists, they just go up to the giant sky thermometer and they take the reading and say, is it hot or cold? No. There is no such thing as a global temperature for the Earth. We all actually, we all know this intuitively. It's colder in the winter, it's warmer in the summer. It's colder in the Arctic, it's warmer in the Sahara. You could go up, the temperatures are different at the top of the hills, the bottom of the oceans, or in the Earth's crust, up in the stratosphere. So this is the thing, there isn't actually a global temperature. So what are people saying when they're talking about it? Well, usually they're referring to a graph, something like this, which is called the Global Mean Surface Temperature Anomaly Index. Notice it's not a temperature, it's an index. And even though it has a degree centigrade on the side, on the axis, it's an index, relative. So we're going to talk a little bit about that. But the first thing I need to point out is that a lot of the discussions, particularly the UN's Intergovernmental Panel on Climate Change, the IPCC, if you look at a lot of the data that they're using for their discussions is actually climate models. So in a climate model, a computer model, it is actually very easy to calculate the temperatures at any point in your model world. But if you're living in the real world, that's a lot harder, because if you want to take a measurement, you actually have to go out and take that measurement. And if you want to find out measurements in the past, you have to go and find out and hope that somebody in the past has taken those measurements, and then you're going to have to look at correcting for that. And so that's something that we're going to be talking about here. What do you do dealing with these old records that were taken from 100 years ago, and they were taken by different observers, and how do you account for that? Yeah, now, so we even have this problem of even the Celsius scale and the Fahrenheit scale were only invented in the 1700s. There were some slightly older ones like the Rankine and everything, but that already puts a limit to how far back these records were going. But there was another limit, is that people weren't systematically recording measurements. It was only really kind of in the late 19th century that you would start getting a lot of records being taken. And usually these were amateurs, and mostly Europe and North America. Now there's a big shift, improvements over recent years. So in particular, in 1957-58, there was the International Geophysical Year, and this was at the height of the Cold War. But scientists around the world were saying, look, we want to collaborate. We should be monitoring. If we're supposed to be studying the Earth system, we need to have the data. So they organized this thing where let's start taking measurements at locations all around the world. And so there's a huge increase of data from 1958 onwards. One of the things that led to as well was Sputnik was the first satellite. And so this then led to, a few decades later, scientists started using satellites. So we have satellite observation from the 70s onwards. Then a big advance that's relevant for us is weather stations. You had an automatic weather station. So people were then able to start taking remote observations in sites that they weren't really able to take measurements from before. And then here's another thing. thanks to one of the side effects of people in the 90s, as the UN saying we need to do something about climate change as well, they started putting in funding for, hey, well, can we actually record the climate? So people started, there's a lot of funding went into setting up measurements to start looking from the 1990s onwards. Now, so in this talk, we are mostly going to talk about the global mean surface temperature anomaly index, and we're mostly going to be talking about the land surface temperature, which is based on the weather stations. If we have time at the very end, I'll mention a little bit briefly about the other component, which is the marine observations. But the key bit I want you to get from this is, if you look at it, that's the main data that we're looking at, and it's from 1850 onwards. Most of the other climate data is actually going from the 50s onwards or the 70s onwards. So if you want to look at it, you're stuck with these weather station observations. Now, sometimes people will talk about using paleoclimate. Remember I was saying about 100,000 years and all of this. How did they come from that? And so there is, we could do a whole other talk on the temperature proxies, and that's a lot of ongoing. But just to give a bit of context, so these temperature proxies, you're talking of the classic is the tree rings. So if you have a trees that are in what's called a temperature sensitive region, basically a cold region, if you have a hot summer, then you'll have a thicker ring width than if you in a cold summer. And so you could use this as a kind of a proxy for the temperature. So you have other ones, you have the ice cores, the lake sediments, the speleothems, particularly the stalagmites. But the key bit is, these are not thermometers. They don't look like thermometers, do they? No, like you could call it maybe a treemometer. So you can't mix and match them, but nonetheless, they do give us a longer perspective for looking at longer things as a relative aspect. And so I just talk about brief detour, just to give it, a lot of you might be familiar with the infamous reconstruction by Michael Mann and colleagues. It's called the hockey stick. So that's the graph at the top, is the hockey stick. Now we could have others, but just to show you, there was other estimates, like for instance Moberg et al. And this is ongoing things, but most of the discussion is about how the current warm period refers to the medieval warm period. But for our context, I want you to notice that even though there's this debate, all of them are showing that the late 19th century was the end of the Little Ice Age, a relatively cool period. So we're starting our instrumental records in a relatively cool period known as the Little Ice Age. So now let's get back onto our land surface temperatures. So there's different data sets. They're mostly using similar sources, but we have the main one that we're looking at is NOAA. This is the US, NOAA's Global Historical Climatology Network, or GHCN. Now version 3 built on version 2, which built on version 1, going back to the 90s. But in 2018, they abandoned a data and they reconstructed a new data set, which is version 4. But like most of our work dealing with this was on version 3, and so we will talk about this. And so it had a lot of advantages. One of them was that it included urbanization metrics. But they had 7,200 stations. But a big thing is, a lot of them were actually, in the longest records were all in the US. So it's like, it's not a uniform representation. Most of our data, going back past, as I mentioned before, is in the Europe and North America. But the other thing is, this is the station counts by year. And you can see that there was a big amount of data from 1950 up to 1990. There was a drop-off in 1990. And the very limited data for 1850 to the early 20th century. So when people are doing it, remember that. We're going into... Now, so just a quick note on the current version is version 4. And there's like now 20,000 stations. But a key bit is, more than half of the long records are in the US, which was already a well-covered region. So it is an improvement, but it's not backwards compatible with the previous one, and it's not as amazing as people are thinking. So what are we talking of a temperature record? So this is a Stephenson screen. Fans of literature, the Robert Louis Stevenson, who wrote Treasure Island, his father invented the Stephenson screen. And so the idea is, if you're doing outdoor measurements, and a lot of the early measurements were indoors, if you're going outdoors, you don't want it to be exposed to the elements, to the wind and the rain. And so you need it kind of in a box. But you also don't want that box to be closed, so you want to allow some circulation. So that's why we have these Stephenson screen, and there's other screens that you could use as well. The oldest records, out of convenience, there was what's called a maximum minimum thermometer system, and that's actually 2 thermometers, and each thermometer has a little drop beside it. And so the maximum temperature, when you reset it as time during the day, if it reaches a higher temperature, it'll push that ball up, and the same with the minimum, will push it down. So when you go and check it a day later, you can see the maximum temperature and the minimum temperature that was reached. And then by convention, people will go and they take the average of the two and say that's the average for the day. Now clearly that's not the average, but by convention it is an average. And so people say, well, let's take that, and then we average it, each one for the month, and then you say that's the average for the month. And then we say, no, so this is the key bit we do is, when we're looking at trying to go to global, how do you do that? Okay, so the temperature, we convert it into temperature anomalies. So what we do is, for each station, we go and we take the average for a 30-year period, say, and then you say, is this hotter or colder than average? And then you convert it into a temperature anomaly. So how do you convert that? Again, reminder, there is no global temperature, but what you can do is, if you have all of these stations around the world, and they each are showing these station anomalies, and they're showing similar ups and downs, maybe you can average those together, and that's what people do. And there's different methods you can do it. The most easiest to understand, but they give similar results to you. You have cryoging and spatial interpolation, but gridding is the easiest. They take, for every month, they grid all of the stations, and for a given grid, they look and say, what are the station anomalies for all the ones available here? You average it. Then you do an area-weighted average of the grids, and that gives you your global land surface temperature anomaly. Again, it's not a direct measurement, no sky thermometer. But nonetheless, that's what we're dealing with. And so, so what we're going to talk about now is the meaty part of it, is that what are called non-climatic biases. So those temperature records we'll talk about have non-climatic biases. And then we're going to talk about the solution that supposedly has been done, which is called temperature homogenization. So we'll talk about these first. So what do I mean by non-climatic biases? Well, I don't know if you can see this. If it's hard to read it, maybe if you're watching online, you can pause and take a look at it. But what we have is, if we look at say you had your Stephenson screen, and you had a thermometer, you changed your system after a period of time. The new system, the new thermometer might actually be better and giving more accurate readings, but it will be giving a higher or lower temperature than it would have been doing before. So that will introduce a jump in the temperature record. And so then you could also have the station might be moved from one location, it might be moved to a hotter or a colder region. And so that could introduce a bias as well. Now, these are step biases, we call them, because they're jump before and after. So you could also have, for instance, you notice that there are trees that are growing up around the thermometer screen. The observers say, hey, this is cooling our temperature, so we need to remove that. So they cut down the trees or the vegetation. And that's great, but then that introduces a jump. Meanwhile, you might have buildings are growing up around the area as well. So what we do is there's the other biases. These are gradual biases. Remember, the trees, they grew up over time, so that bias came in slowly. So that could introduce a long-term cooling. But the other one we want to talk about is the urbanization bias. So urban areas are warmer than the surrounding countryside, and if you have a car, either thermometer in your car, you might notice as you go into an urban city and leave it, you might find a rise going in and out on average. So the thing is, that's a real local climate change, and it's a real human-caused climate change, but it's local. It's not representative of the climate from the surround. So if you are trying to use your urban stations to calculate global temperatures, you need to acknowledge the urban heat island, urbanization bias. Now, this is something that I've observed, is that when you read the literature, people, when the scientists identify that there is a long-term cooling bias that needs to add warming to the records. This is considered very, very important, and anybody that's not doing that is using bad data. But as soon as somebody says, well, maybe there's a warming bias that we need to correct for, then the literature says, oh, that's not too important, and you're overplaying it, and we don't need to bother. So it's an interesting bias in the types of biases that are considered biases. Okay, so let's just So let's look at the temperature distribution. They have now. So I've plotted here urban stations in red and the most rural are in green. And you can see we have a lot of stations, and we actually have for the modern era, and we even have a lot of green stations, of rural stations. But when you go back to the earlier parts of the records, you can find that, again, mostly just Europe, North America, but most of those stations are now urbanized. And so that leads to a problem when we're looking at the earlier parts of the record, even though urbanization bias is becoming a stronger problem as we go further back. And it's even worse if you go back to the 18th century. But this counterintuitive problem, we have a lot more rural data now, thanks to the automatic systems and everything like that. If we want to look at how things have changed since the 19th century, most of the data is urban now. So it's an inverse problem to what you think of. Now, this was how did I get into this? Well, I started working with my father, Dr. Michael Connolly, about 15 years ago on this, in our spare time. And unfortunately, he passed away unexpectedly last year. But like the work that we were doing initially, we worked for like 5 years just on our own, and we decided, we found a lot of results, and we decided to publish our work, but we realized that there was so much work and it would get against the narrative that we wouldn't be able to get it published in peer-reviewed journals. But we said we want to let the public know. So we set up the Open Peer Review Journal, and we just said, let's upload 8 of our papers and let the public peer review it. So we published them as working papers and allowed people to share them and look at them. Now, one of the papers that's relevant for us is, you remember I was saying how the people are saying, oh, the urban heat island isn't a big problem because it's a warming bias, don't worry about it. We went through every single paper we could find that made that case. And we went and we said, okay, let's look at your data. And we found that in every single case, we found that no, there was flaws in their analysis and or their conclusions. And so that it is a problem. And trying to dismiss it doesn't work. But one of the groups, the only group that is explicitly correcting for urbanization bias, is the NASA Goddard Institute of Space Studies, NASA GISS. So they had developed this algorithm that they said, oh, this should correct for urbanization bias. So since we said, okay, let's look at it. So it downloaded all of the adjustments and spent a long time analyzing it and finding that the results were, it turns out that nobody seems to have stress tested, is this actually working? and until we did. And so just to give you an example, we just took the largest metropolises in the world and we looked at all of the weather stations in them and we just averaged them together, the adjustments they were doing, and we got this graph on the green. So the average adjustments were nothing up to 1895, and then they were correcting for a warming bias, and then in 1990 it stops basically. So they were not correcting, so they were cooling from 1895 up to 1990 and then stopping. And if you think about that, you'll realise that's effectively adding warming to the GISS record from 1990 onwards. So why did this happening? They only give 2 examples of stations, Phoenix, Arizona in the US, that they applied there as case studies, and the other is Tokyo. So we looked at Tokyo. Turns out that the top line is the unadjusted. What they do is they identify 3 rural stations that are nearby, and they get the average of that, and they say any difference between that, maybe that's urbanization bias, and so they fit it with these 2 straight lines. And so the black dots on the bottom graph are the difference between the rural and the average, and the red line is their adjustment. So if you look at this, you can see that the red line fits within the black dots all the way up to 1990, and then the red line just flat lines. But we have the hollow lines showing the differences. Why did they stop the adjustments? Well, the requirement was that you needed to have at least 3 rural stations to calculate it. And so do you remember I said there was a drop-off in 1990? Well, one of the rurals, it's mostly in the rural stations, so that dropped off, so they no longer had 3 stations, so they stopped the correction. Okay, now so then another aspect is how do they identify the rural? So in 2010, they switched to using night brightness, the amount of street lights associated with an area. So just as an example, we showcased Riyadh in the Middle East, and they said they had 3 rural stations, apparently rural, that they used for calculating. And now Baghdad, maybe because of the Iraq wars, the night brightness wasn't as bright as it used to be, but Kuwait International Airport, why is that considered rural? And it turns out the coordinates they had for the station were off by 30 kilometres. They had it actually out in the middle of the sea. So the night brightness, the street lights in the middle of the ocean or sea are not very bright. So they said, so their analysis effectively said, well, Riyadh is showing the same trends as Kuwait International Airport, and Kuwait International Airport is the most rural station in the world, so we don't need to correct for that. So in 2015, we were, my parents and I we went over to visit Willie Soon, who will be speaking tomorrow, and we're starting a collaboration with him. And so while we were there, we decided to stop off in New York City. And so I had emailed Gavin Schmidt, who was the director of NASA GISS, and we said, look, here's our paper. We're finding lots of problems in your adjustments. Do you want to discuss it with us? See, are we wrong? And because if we're wrong, we want to improve. And he said, well, he's busy, but he kindly asked Rita Rueda, who's the expert in that data series, to meet with us. We spent the afternoon going through with it. Every bit of the thing we said, had you seen this? Had you considered this? No, we hadn't considered this. Is it serious? It could be very serious. Well, you know, are you going to do anything about it? And it's like, at the end of the thing, he said, look, he agreed that he would look carefully, and if we had made any mistake he could find, he'd let us know. And if NASA was going to update it in light of those mistakes, he'd let us know. So that was in 2015. I was still waiting. Anyway, another non-climatic biases I might mention is the sighting biases, and this is thanks to Anthony Watts and a lot of volunteers who went and they surveyed the stations. So this often gets mixed up with the urban heat island. They're separate things. You can have a well-sighted urban station and a poorly sighted rural station. But the basic idea is within 100 meters, are dealing, are at least 30 meters. You want to have low vegetation. You don't want to have concrete or asphalt. You don't want to have trees. You don't want to have buildings. And so the one on the top left is well sighted, very good sighted. The one on the right, you can see off in the distance, within 30 meters, there's a car park and buildings. The bottom left, there is the exhaust of an air conditioning unit less than 10 feet away from it. So that's, and it's surrounded by things. And then you have ones that are on top of a roof. So the thing is, when we looked at it turns out that for the US at least, the majority of those stations are poorly sited, and only a small percentage of them are well sited. And so when we looked at the temperature trends of the well-sited and the rural, look at the one in the middle, the bar charts in the middle, we found that the bad-sited showed twice the warming of the good-sited. But after homogenization, they all moved up. The well-sited had warming added until they met the station average, which was that of the poor stations. So what's homogenization? So there are a number of different mechanisms, different techniques. Most of them have similarities. The main one that we've talked about, but others are similar, is that NOAA switched in 2009. They developed the Pairwise Homogenization algorithm, PHA, and that's the one that NOAA have been using, and a lot of others have been looking at it. And so this is quite a complex thing. I'll try and break it down. But just imagine you remember a station bias, the top graph on the left, you can see that looks like there's a big jump, a station move, or a step bias. Can you see that on the left? You have, this is, and imagine things. But how do you know? How do you know it's not real? What is it? So, well, one way is you can look at the neighbors, and you see none of the neighbors are showing that jump, so probably it's non-climatic. But to be specific, what they do is they take the difference between they take the difference between your target station and each neighbour, and then you look statistically, is there a breakpoint, what they call? And if there is, and it's just in the target station, you do a statistical test and you say, that's a non-climatic bias. And then what they do is say, well, let's look at the difference before and after that breakpoint, and we'll apply an adjustment to bring it in line. So, yeah, and so then that's called that's what you're doing is you then, at the end of it, the whole network is homogenized, okay? So the problem is, how do we know that this adjustment is real or not, or should be doing it? Because if we knew what the real temperatures were, we wouldn't need to apply these adjustments. So it's very much a bootstrapping thing where we kind of said, we think this might improve it, and so we're going to do it. But okay, so one of the main things was there was a number of groups developed what are called benchmarking experiments, and this one was particularly led by Victor Fedova, who is somebody who I disagreed with it a lot, but I also agreed with it. We were quite friendly towards the end, but sadly he passed away during COVID suddenly. And so, but he did this thing where what he would do is he would create synthetic temperature records, and then he would apply artificial adjustments, and then he would ask the homogenization groups, can you identify it? And they actually did quite a good job of identifying his breakpoints. And so on that basis, he said, wow, homogenization improves the data. So the problem is that we were looking and saying, but it's not real data, that's synthetic data. So what we wanted to do is say, can we actually see how are these adjustments applying to real data? And so what we did is in 2022, we did this collaboration, and I'll just mention that this was a huge collaboration across Europe, and for the record, a lot of the co-authors that we did, they don't necessarily agree with my views on climate change, but they're good scientists, and as a scientist, we can collaborate. We don't have to agree with everything to do it. So they all agreed with the analysis that we had done, and we came to the same conclusion that they were all shocked. And so the things we wanted to know is what homogenization, just for Europe as a case study, but it's a large thing, what adjustments is NOAA applying, and how do these compare to what is called a station history metadata? So when the observers were recording their temperatures, they were also recording that there might have been, we changed the thermometer on the 5th of December 1962. Or we moved the station. So those were recorded. And then can we see, that could have introduced non-climatic bias. This looks a bit of a mess, but if you want to go, you can go to NOAA's website and you can download the files. And so the files, the key bits you're looking at here are those ones there. And the .qcu is the unadjusted, and the .qcf is the homogenized. And the thing is, though, every day they rerun the calculations, but they don't archive them. But my colleague, Peter, who's a retired engineer, he had been archiving it. So he had started downloading, he downloaded the files in 2011, and then he updated it. He wanted to check something. He downloaded a new version and noticed that the adjustments had changed. And he said, that's strange. So he said, I'd better download it every week. And then he said, I'm going to download it every day. So when we started this collaboration, we downloaded thousands of versions of NOAA's adjustments that had been done. And so let's talk about the station history metadata. If you look at, this is just an example, Holzhausen, you can see January 1861, that station moved. And then in April 1997, there was a change in instrumentation. So these are not widely known, and it's only in recent years that people have started digitizing it. But that should be a good test. Is this an actual event that has taken place? So just to give you an idea, for Czech in the Czech Republic, this is an urban station, and the vertical blue dash lines, those are documented station events. So let's see how it does. So we have nearly 2,000 adjustments, but each of the sets of adjustments that NOAA statistically had been applying, each time you run it, it was giving you different adjustments. Now sometimes these are kind of similar. Those are the adjustments. That was applied 6% of the time. This was slightly different, applied 1% at the time. But you can see different adjustments applied. So if you download the data set on a Tuesday, you might have a different temperature record for 1856 than if you download it on a Wednesday. That's what we're talking about. And so the other thing is that we found that some of the breakpoints that NOAA was identifying were consistently identified. And encouragingly, the 1955 one, it applied adjustment every time. And also, interestingly, in 2010, which was a non-documented event, but it keeps finding it. So maybe there was an undocumented event. But a lot of the adjustments were inconsistent. They'd be gone, you'd have it on Monday, it'd be gone on Tuesday. So we looked at this. It's not just CHEP. We looked at over 800 stations that we had station history metadata, and what we found is only 17% of the adjustments were consistently applied, and only 19% actually corresponded with a documented event. So we mentioned Schumacher said a man who uses an imaginary map thinking that it is a true one is likely to be worse off than someone with no map at all. Just think about this. How do we know if we are applying an adjustment and the adjustment is different the next day? Which one do we apply? Do we apply Tuesdays or Thursdays? Or none of them? I would say, until you figure that out, none of them. But we also, a separate paper, this is looking at a statistical problem. It's not just for PHA, it's for all of them. It's the urban blending problem. So the problem is, it's a statistical thing. Remember I was saying, essentially the homogenization process, at the end of it, you have all of the temperature records are homogeneous. It's like putting them all into a blender. At the end, they all show the same thing, but it doesn't remove the non-climatic biases. So this is technical. You can read the paper if you want more, but basic idea is, remember I was saying they would apply adjustments based on the difference before and after. So if you are using an urban station as an urban neighbour, that urban neighbour will have an urban warming trend. So if you look at the difference before and after, that will add a warming to the adjustment. And vice versa, you actually end up with the most urban have a adjustment. So essentially what happens is all of the stations after homogenization converge on the average of the network, which is more urbanized than rural. And so you have urban blending. Now, if you then compare the rural homogenized to the urban, there's very little difference because they've had it in. So we did a detailed analysis, and I'll just briefly show that we looked at Japan and the US, and Japan is a highly urbanized country. And so, okay, so this is a messy graph, but essentially that's the trends. The warming or cooling trends. If it's above red, it's warming. If it's cool. And if you go from left to right, we've ranked them all from the left is the most rural and the right is the most urban. And you notice the way that the blue line is going up and to the right. So you're going from cooling for the most rural to warming. Well, after homogenization, what happens? All of the rural get warming added and the urban get cooling, and so they all end up with the average of the network. Now, so in the paper, we do suggest particular mechanisms for how you could correct for that moving forward, solution 1 and 2, which you can look at it. But we also said, is there another way? And we had been working on this. This is accumulation of a 9-year project involving, in the end, 45 scientists. A couple of them are here, of my colleagues are here. And we did a whole thing. We said, can we just not use this automated homogenization and identify rural stations and correct for them? And we did. And the difference is our rural record is the one on the bottom right, and the standard one is on the left. And so you can see they're slightly different. Now, both of them show warming, but if you look at the standard one shows almost a continuous warming with a bit up and down, whereas the rural shows warming, cooling, warming. It's almost cyclical, which suggests maybe more natural. And so I'll skip over these things here, but we also looked at the oceans and the sea surface temperatures. There's very little data before 1950s for sea surface temperature. It's mostly in the northern hemisphere. There's also changes in instrumentation, particularly the buckets to the engine room intake. And if you take, Kennedy et al. Showed that if you take all of the engine room intake, they show different trends from the bucket measurements. So which one is correct? I don't know. But if you average them all together, you can get a homogeneous thing. But we also, our records show similarities to all of the other ones. So just to conclude, global warming, what does it say? 20th century is warmer than the late 19th century. So you agree, there's global warming. Yes, but that was after the Little Ice Age. But it's been warming since the 70s. Yeah, but it was cooling from the 40s to the 70s. Oh, but there's lots of climate data, the Arctic sea ice, all of this stuff. Yeah. That begins in the 50s or the 70s or more recent. You're a climate denier. Okay, right. So just last two, moving forward, that project, the 9-year project, was using version 3. We are planning to move forward to version 4. Problem is, NOAA decided to drop urban ratings. So we're having to do that. So we've done some preliminary work already. I also want to give a shout out to my brother, Stephen, who independently just recently set up a website, climate.com, and you can just have a look at it. It's very good. You can look at each of the temperature records. And also on X, there's a pseudonymous Orwell 2024. He's also done a similar attempt at it. We want to use those station history metadata is now being digitized, and we've been compiling a lot. We think that we should be incorporating this information. Also using Peter's archive to identify some of the non-documented events, and then using solutions 1 or 2, and also looking at sighting bias. So ways you can have it. If you like what we're doing, the first thing is go to our website, ceres-science.com, And the very first thing is you can sign up for a mailing list and keep up to date whenever we have new updates. We also have a YouTube channel that we're trying to grow and expand on. Go to our news archive, share any of the stories, share our publications, and if you can, we rely on donations, so if you could support us there. Thank you. Okay, thank you. Do I stay here?